Greetings and welcome to Distiller. In the previous class, we discussed about variable mass systems. So in that case, we discussed that the equation of state for ideal gases is going to be followed as this. P1 V1 by M1 T1 is equal to P2 V2 by M2 T2, which can also be written as P1 V1 by N1 T1, where N1 is the number of moles, up is equal to P2 V2 by N2 T2. This is the general equation of state for ideal gases with variable mass, right? In variable mass systems. Apart from that, we can also form energy balance. We can also form energy balance equations depending on whether the transfer is taking place at constant pressure or at constant volume. So the transfer is taking place at constant volume, then in that case, heat or basically energy transferred at constant volume is equal to internal energy difference. That is M1 into specific internal energy minus M2 into specific internal energy. Initial minus final. All right. Then energy transfer at constant pressure. Energy transfer at constant pressure is equal to enthalpy difference, which is M1H1 minus M2H2. So this is what we discussed, and we discussed various problems based on these concepts, right? All right. So today we'll start our class with this problem. A gas obeys PV minus B equals to RT. The work obtained from reversible isothermal expansion of 1 mole of this gas from an initial volume of VI to final volume of VF is. So this is quite an easy question. It came in GATE 2004. So when we talk about a gas with this equation of state, PV minus B is equal to RT. All right, this is the equation of state. So from here, we can get P is equal to RT upon V minus B, or we can even get V is equal to RT by P minus RT by P plus B, right? RT by P plus B. All right, so these two things we can get. All right, now we know that work done, or I should say the modulus of work done for any condition is equal to integral of P dV from Vi to Vf. This is what we discussed in one of the classes, one of the lectures, right? So integral of P dV from initial volume to final volume, that, or actually I should say smaller volume to larger volume, right? So in this case, since expansion is taking place, therefore initial volume is going to be smaller. So Vi to Vf, right? So now in that case, since it's modulus of work done, so we are going to take integral of P dV, and that when we solve, P is equal to RT upon V minus B. So this is RT dV upon V minus B from Vi to Vf, which when integrated gives you ln V minus B, ln V minus B, just a minute. When integrated, it gives you RT ln V minus B. This we have to integrate, from lower limit of Vi to upper limit of Vf. So this comes as RT ln Vf minus B upon Vi minus B. All right. So this is option number D. All right. Vf minus B upon Vi minus B. Why have I directly taken option number D? Because it is expansion process. So work done is going to be positive of W, positive of mod W. So that is going to be this as it is. If it would have been in compression, work done in compression, then in that case, we would have taken negative. We would have taken negative of this thing. All right. In case this would have been the condition. All right. This would have been the work done. Okay. Now, the question is that why did we use this? Why did we get this? So in case, if I change the question and I say that do it from Pi to Ps. All right. So if you solve using this, then it is going to be quite lengthy. So if I give you that, solve it from Pi to Pf, then since it is expansion, then definitely Pi is going to be larger and Pf is going to be smaller. All right, smaller, larger. All right. So now we can write this particular problem as we could have done it in this way, that we could have, this is not a part of the question, I'm just telling, in case we could have got pressures. So in that case, we would have taken dV. So dV is equal to minus RT by P square dP. All right, this is this is dV. So integral of P dV can also be written as integral of minus RT by P square into P dP. So this is basically minus integral RT by P dP. All right, minus RT by P dP. Now, since here we integrate from smaller volume to larger volume, therefore we are going to integrate from larger pressure, that is Pi to Pf. All right, larger pressure to smaller pressure, Pf. Okay, so that comes out as minus RT ln Pf by Pi, right, which can be written as RT ln Pi by Pf. This is mod W. This is mod W. So if you, since it is work in expansion, so this is going to be this. So this is what we get. All right. This is what we get as answer. So in case pressures would have been given, then this would have been the answer. And you can actually get it from here as well, but it would involve just one or two more steps. For example, over here, Vf minus B can be written as RT by Pf, right? So over here, we would have written in place of Vf minus B, we would have written RT by Pf, and in place of Vi minus B, would have written RT by Pi. That's all. All right, so it would have come as ln RT ln Pi by Pf. All right, so you can calculate it in both the ways. All right, you can get it in both the ways. So even if the pressures would have been given instead of volumes, then also this question could be easily solved. All right, so with this, we move on to today's topic, that is the equations of state. Now, equations of state is a very big, very vast topic. So I have divided this into two: equation of states 1 and equation of states 2. All right, and apart from that, still there would be certain things that would be left untouched. So we'll be covering that further. All right, so equation of state. We are all very well aware of one equation of state, that is ideal gas law. All right, the ideal gas equation of state, which relates pressure, volume, N, which is the number of moles, and temperature, right? It relates these four, right? This is the ideal gas law. And we have already discussed that we study about ideal gas law because even if we talk about real systems, then they somewhat come close to ideal systems, right? And the second thing that we discussed was that all substances, irrespective of their properties, they are going to reduce to the ideal gas model at low pressure and high temperature. So therefore, if P tends to 0, that is very low pressure, and T tends to infinity, very high temperature, the system will reduce to an ideal gas equation. Thus, relating every substance to the ideal gas law is very much justifiable. All right. So ideal gas law is definitely very important. But we also need to study about real gas systems in order to deal with moderate temperature pressure conditions. So the general thing about equation of state is that any gas can be written as a function of pressure, volume, and temperature. The equation of state for any gas, it can be written as a function of pressure, volume, and temperature. So it can be represented in this form. So for example, even if we consider the ideal gas equation of state, so this can be written as PV minus nRT is equal to 0. So PV minus nRT is basically a function of pressure, volume, and temperature. All right. And in case of variable mass systems, of course, even number of moles can be considered. Right. So that is there. So this implies that irrespective of the type of system, pressure, volume, and temperature are always going to be interdependent. They're always going to be interdependent. So in that case, the above expression can be used to derive another very important relation between pressure, volume, and temperature. That is dou P by dou V at constant temperature into dou V by dou T at constant pressure into dou T by dou P at constant volume. It's not 0, it is -1. All right, it is -1. So if you can remember this as this, that we can write pressure, volume, temperature, and it goes in a cycle. So dou P by dou V, keeping temperature constant, into dou V by dou T. So dou P by dou V, then dou V by dou T. So dou V by dou T, keeping pressure constant, into now dou T by dou P, keeping volume constant, can be written as -1. So this is a very important relation that can help you further. All right, this is going to help you further in chemical engineering thermodynamics as well. So keep this in mind. Dou P by dou V at constant temperature into dou V by dou T at constant pressure into dou T by dou P at constant volume is equal to -1. Now, let's understand PVT behavior of pure fluids. So when we talk about pure fluids, they are, suppose if we are talking about liquid and vapor, all right, liquid vapor consideration. All right, so in that case, when suppose I'm taking a particular fluid at state A, all right, I'm taking a particular liquid at state A. So here it is liquid. Now what I'm doing, I'm reducing the pressure. I'm reducing the pressure on this. So as I reduce the pressure, it moves from A to B. All right, it moves from A to B. All right, now as you can see, I've reduced the pressure so much, but still the volume change has been almost negligible. This is one reason why we usually take liquids to be incompressible. All right, this is one reason why we usually take liquids to be incompressible, because generally with a great increase or decrease in pressure, the volume change is very less. All right, so that is why liquids we generally consider as incompressible. That is one of very important assumptions that is taken. Then at state B, it becomes saturated liquid, something that we studied already in steam, but over there we saw the temperature versus enthalpy diagram. This is the pressure versus volume diagram. So over here, this is a state of saturated liquid. All right. Then from B to D, over there we had in the temperature versus enthalpy diagram, if you people remember, we had this for liquid. So liquid, suppose it starts from here. So liquid, then over here, S used to be saturated liquid. Then from here, T used to be saturated vapor. And then further superheating. All right. So this was the temperature entropy, temperature versus enthalpy diagram. So this is the same diagram, just in pressure versus volume. So over here, my temperature is kept constant, pressure is varying. All right. But over here, as you can see, even in the temperature enthalpy diagram, when vapor and liquid both are in equilibrium, then both pressure and temperature are constant. So over here as well, although temperature is already constant, we have kept pressure constant as well from B to D. So in B to D, the state is liquid plus vapor, right? In B to D, the state is liquid plus vapor. And then finally, it is decreasing. The pressure is decreasing, and with the decrease in pressure, you can see that the volume change is significant enough. So E is basically any state in vapor. All right. So now this is basically an isotherm. Isotherm as in temperature constant. All right, temperature is constant. So now what we are doing is, if we suppose increase the temperature, then this curve would shift towards the top. All right, it would slightly shift up. All right, so this is another curve that has been drawn at a higher temperature. All right. Another curve that has been drawn at a higher temperature. All right. And so on. If we keep, so as you can see, the gap, this line between B and D is reducing. All right. B and D is reducing. So basically we have made this curve, this shape that you can see. This curve is actually a saturation curve. This curve is saturation curve. So let me tell you about the saturation curve. So saturation curve is something like this. All right. Saturation curve is something like this. So towards, you can see the peak of the saturation curve is somewhere here. All right. Peak of the saturation curve is somewhere here. So towards this side of the peak is saturated liquid states. All right. So these are my states at different temperature. This is at different temperature. This is at different temperature. This at different temperature, and so on. All right. So all these states are at different temperatures. So these are my saturated liquids. And towards this side of the peak, you find saturated vapor. So this is my saturated vapor at different temperature, and at different temperature, and so on. So if you take this curve, all right, you take the saturation curve and you mark a point. This is my peak. So you mark a point here. Let's say here the temperature is, let's call it A. And at A, the temperature is, let's say, 220 degrees Celsius. All right, 220 degrees Celsius. So from here, if you draw a straight line, then over here, you'll find, let's call it B. The temperature is going to be the same, and B is going to be saturated vapor. All right, saturated vapor. So this is the significance of the saturation curve. All right, this is the significance of the saturation curve. So towards one side, or basically towards this side of, towards the left of the peak, you find saturated liquid, and at the same temperature on same pressure towards the right, you'll find the saturated vapor. All right, something like that. Now, as we can observe from this curve, that as it is going up, that means as the temperature is going up, as the temperature is rising, what happens? The gap between the saturated liquid and saturated vapor, it is reducing, right? So here the gap is lesser, here it is even lesser, here lesser, here even lesser, and here the gap has almost become zero, and actually the vapor liquid state occur only at a particular point. All right. And then if you further increase the temperature, there would be no vapor liquid state. Directly you will go from liquid to vapor. Or I should say, you will not even have a liquid state. You will always have a gas state. All right, that is a thing. So you'll always have a gas state above this temperature. If you raise this, then you will only have gas. If you'll raise the temperature, then you will only have gas. Okay, so this point where you get the peak of the saturation curve, this point is known as the critical point. All right, this point is known as critical point. And the pressure, volume, and temperature at this point are considered as critical parameters. All right, so PC will be called as critical pressure, VC will be called as critical volume, and TC will be called as critical temperature. All right, TC will be called as critical temperature. So as the temperature rises, the vapor and this gap between vapor and liquid state, it reduces, and finally after a particular point the gap becomes zero. So at that temperature where the gap is almost zero, that temperature is known as the critical temperature. Okay, now if you raise the temperature above the critical temperature, you will not have liquid state. All right, you will not have liquid state. For example, if let's take any gas, say gas A, and if its temperature is, critical temperature is, let's say 500 degrees Celsius. Okay, so now if my gas is at 400 degrees Celsius, I can get liquid and vapor. If I have gas at 450 degrees Celsius, I can get liquid and vapor. Even at 500 degrees Celsius, I can have liquid and vapor both. But if I take temperature greater than 500, let's say 550 degrees Celsius. So at 550 degrees Celsius, you will not have gas at all. You'll not have, you'll not have liquid at all. You'll only have gas. So if you raise the temperature above the critical temperature, you'll not be able to get liquid. So in that case, you'll only have to reduce the temperature, then only you'll be able to get gas. Otherwise, no matter how much you reduce the pressure, no matter how much you reduce the volume, no matter how much you increase the pressure, the substance, you're not going to get it in the gas form. All right. The substance is not going to be in the liquid form. All right. You're always going to get the substance in gas form. So if you raise the temperature above critical temperature, then no matter how high the pressure is or how low the volume is, you are going to get the substance in gas form only. Okay. So in order to liquefy the gas, you'll have to reduce the temperature. Okay. So all these informations we've already discussed: liquid phase, saturated liquid, saturated vapor. All right. So this is basically my behavior of pure fluids. I've told you these things because we'll further be dealing with critical temperature, critical pressure, critical volume. So this is quite important while we are dealing with these things. Okay. Now we come to the real gas equation of state. The first real gas equation of state we'll be dealing with Vander Waals equation of state. All right. We'll be dealing with Vander Waals equation of state. So Vander Waals equation of state takes into account the pressure correction factor and volume correction factor. So basically, suppose if I have a gas with these two molecules. All right, I have a gas with these two molecules. Now, there would be some interaction between these two, right? There would be some interactive forces between these two. All right. Now, this interactive force is neglected in the ideal gas equation, but we account for these molecular interactions. All right. We account for these molecular interactions because now the gas is at moderate pressure and moderate temperature. So the molecules are close enough. All right. So we need to account for these interactions. All right. So we get the pressure correction term and volume correction term. The pressure correction term is A by V square in the ideal gas equation. P V equals to RT for 1 mole. All right. So in that, we are including a pressure correction term, which is A by V square. And we are including a volume correction term, which is B. Over here, V is the molar volume. All right, V is the molar volume. So keep your equation, always remember your equation in this form only. Otherwise, it is going to get very complicated further. Okay, so please don't get confused. Okay, so P plus A by V square into V minus V is equal to RT. This is the Vander Waals equation of state. All right, this is the Vander Waals equation of state. So if we want to evaluate the Vander Waals constants, that is A and B, then we can use these two equations: 27 by 64 R square TC square upon PC and 1 by 8 R TC by PC. This is A and B. All right. And similarly, using the Vander Waals constants, we can get critical pressure, critical temperature, and critical volume. All right. So these two applications also, these two things can also be interrelated. All right. Now, the main thing, the equation of state, the Vander Waals equation of state, it can be simplified and written in this form. All right. It can be simplified and written in this form. So now this form of equation is a cubic equation in volume. All right. This equation is cubic in volume. So since this equation is cubic equation in volume, therefore, when we solve this equation, we'll get three different roots: V1, V2, V3. All right, let's not call it V1, V2, V3. Let's call it VA, VB, and VC. such that VA is less than VB is less than VC. Let us see. All right. Now, the greatest root, that is VC, is going to be volume of gas. All right. Volume of gas. The smallest root is going to be volume of liquid. All right. Volume of liquid. And the third root, that is the one which is in between, that has no significance. All right, that has no significance. So the first, the smallest rule is the volume occupied by liquid at the same pressure and temperature, and the greatest rule is the volume of occupied by gas at the same temperature and pressure. All right, so if you basically increase the temperature above the critical point, then there will be nothing called VA. VA has no significance. You'll only get VC because now it is only gas. All right. So that is it. So you will not be asked about volume of liquid. You'll not be asked to calculate both VA and VB because that's a very complicated procedure. You can definitely calculate only the volume occupied by gas. All right. So in order to calculate the volume occupied by gas, you'll have to definitely solve this equation. All right. And solving a cubic equation is not as simple as solving a quadratic equation, because there you can simply use the rule, the quadratic formula, right? But over here, that's not there, right? So for this, we are going to use a numerical method. So what I'll be using is the Newton-Raphson method. All right. What I'll be using is the Newton-Raphson method. So in the Newton-Raphson method, I'll first of all write my Vander Waals equation in cubic form. All right. And I'll put it equals to 0. All right. I'll put it equals to 0. So when I put this entire thing equals to 0, then this actually becomes an equation FV is equal to 0. This, it takes this form. So an entire LHS, which is equal to 0, we can put it as FV. All right. Then from that, we have to calculate F dash V. All right. From that, we have to calculate F dash V. Once we get FV and F dash V, the next step is take the pressure, take the temperature, take R, and calculate molar volume by ideal gas equation. Molar volume by ideal gas equation, and put it equals to V0 or V0. All right, V0. Now we have FV, we have F dash V, we have V0. Now we are going to find out F of V0. That is, we will substitute everywhere in place of V, we will substitute V0. All right, and we'll find out F of V0. All right, we'll also find out F dash of V0. All right, we'll also find out F dash of V0. Then what we are going to do, we are going to use this formula. Vi plus 1 is equal to Vi minus Fvi by F dash Vi. So over here our Vi is V0. So Vi plus 1 is going to be V1. So from here we are going to get V1 using the formula. All right, we are going to get V1. Now check the difference. All right, check the difference over here. If the difference is small, very small, then we have V1 as the answer. All right. If not, then send it back. All right. Send it back over here. Now you have to find FV1, F dash V1, then find out F2, V2. Then again check, and then again the procedure is going to be repeated. Okay. This has to be repeated till the difference becomes very small. All right. Till the difference becomes very small. That is, it becomes negligible. All right. So for this, I have taken an example. Estimate the molar volume of carbon dioxide at 500 Kelvin and 100 bar using Vander Waals equation. The Vander Waals constants are 0.364 meter to the power 4 Newton per mole square and 4.267 into 10 to the power minus 5 meter cube per mole. So now this becomes a very complicated question along with units and everything. So first of all, take care of units. All right. So first of all, take care of your units. Okay. So we have to decide that which unit do we want pressure to be in, which unit do we want volume to be in, and temperature is of course going to be in 100 in Kelvin. And then based on the units of pressure and volume, we'll decide the value of R to be taken. All right. So pressure here, it is given in 100 bar, but we have not calculated any value as such for that, for R at bar, right? So we'll convert it into ATM. So if we convert 100 bar to ATM, so we are going to convert it. So 100 bar, so we'll first convert it into Pascal. So 10 to the power 5 Pascal upon 1 bar. All right. And then we are going to convert this Pascal. We are going to convert this Pascal into ATM. So 1 ATM upon 101325 Pascal. All right. So we are going to get this. So Pascal and bar. So from here we get pressure is equal to 100 into 10 to the power 5 upon 101325. That is 98.692 ATM. All right. Then volume, since we have to take molar volume, so we could either take liter per mole, or we could take meter cube per mole, or we could take meter cube per kilomole, something like that. All right. Now meter cube per mole might be very small. All right. So calculations might not be very appropriate. So, and liter per mole and meter cube per kilomole, it is one and the same, right? So let's take meter cube per kilomole. All right. So in general, remember that when you take meter cube per mole, then the calculations might get inaccurate because of very small values. So we'll take it as meter cube per kilomole. All right. So on the basis of that R, we have 0.08206 meter cube ATM per kilomole Kelvin. All right. So once we have these values, so we have units of pressure, we have units of volume. Then we are going to decide the units for A and B. So we know the the Vander Waals equation is P plus A by V square times V minus B is equal to RT, right? So from here we can see, from this term, we can see the units of B are same as the units of V. All right, the dimensions of B are same as dimensions of V, which we have taken to be meter cube per kilomole. All right, so since we have we have been given A and B. So B we have given meter cube per mole, so we'll convert it into meter cube per kilomole. So B we have 4.267 into 10 to the power minus 5 meter cube per mole. So that is equal to, so 1 kilomole is equal to 10 to the power 3 moles, right? So this has been converted into meter cube per kilomole. So this is equal to 0.04267. All right, 0.04267. That is B. Okay, meter cube per kilomole. Now, if you see the dimension of A, so from here you can see that dimension of A by V square is same as dimension of P. Hence, the dimension of A is going to be equal to dimension of P into dimension of V square. All right. So the dimensions of P we are taking as ATM, and the units of V we are taking as meter cube per kilomole. So this is going to be meter to the power 6 per kilomole square, right? So right now we have A in meter to the power 4 Newton per mole square. Okay, so I'll write it down over here. A is equal to 0.364 Newton meter to the power 4 per mole square. So first let's convert it into a unit of Pascal into volume square by mole square, right? So that is going to be 0.364. This can be written as Newton per meter square Pascal into meter to the power 6, right? When we multiply and divide by meter square. So this can be written as meter to the power 6 per mole square. Okay, now let's see what all we have to convert. We have meter to the power 6. We only need ATM and kilomole square. So for ATM, we have to convert Pascal to ATM. So 1 ATM upon 101325 Pascal. All right. And mole, so we have 1 mole we have to convert into kilomole. So 1 kilomole into again 1 kilomole, and that is equal to 10 to the power 3 moles, and again 10 to the power 3 moles. So we cancel these terms. All right, we cancel Pascal. So we basically get the result in meter to the power 6, sorry, yeah, ATM meter to the power 6 per kilomole square. So A we are going to get as 3.5924 ATM meter to the power 6 per kilomole square. All right, this is the value of A that we are going to get. So we have got A and B in the desired units. We have decided the units we are going to use for pressure and volume. All right, and we have also decided the value of R that has to be used. So now we'll move on to solve our question. So we have P plus A by V square times V minus B is equal to RT, which in its cubic form can be written as PV cube minus RT plus BP times V square plus AV minus AB is equal to 0. All right. So when I substitute the values of pressure, R, temperature, B, and A, I'm going to get my equation as 98.692 V cube minus 45.24 V square plus 3.5924 V minus 0.1533. All right. So this basically I'll take as f of v. All right. This I'll take as f of v. Okay. Now the next step was to differentiate this. So we'll find f dash v. So f dash v from this becomes 296.076 v square minus 90.48 v plus 3.5924. All right, we have got f dash of v. All right, now the next step was to calculate v naught, which is basically the ideal volume. All right, that is the ideal volume. So that is equal to RT by P. So we have the values of R, we have of T and P. So we get V naught is equal to 0.41574 meter cube per kilomole. All right, meter cube per kilomole. So that is V naught. All right, you have got V naught. All right, so from V naught, you need to calculate f of V naught and f dash of V naught. All right, once you get V naught, then you need to calculate f of V naught and f dash of V naught. So f of V naught is 0.613 and f dash of V naught is 17.15. All right, so from here, you'll get V1. V1, which is equal to V naught minus f V naught upon F dash V1, right? Because Vi plus 1 is equal to Vi minus FVi upon F dash Vi. All right. This is the Newton-Raphson method, right? So over here, I was 0. So we have got I plus 1 is equal to 1. All right. So when we solve this equation, we'll get V1 is equal to 0.38 meter cube per kilomole. Now, if you see, the ideal volume was 0.415 and this is 0.38. So there's quite a difference. So we'll move on and find V2 for this. All right. So V2 is equal to V1 minus F V1 upon F dash V1. So first let's find F V1 and F dash V1. So F V1 is 0.095 and F dash V1 is 11.97. All right. So from here we get V2 is equal to 0.372 meter cube per kilomole. So basically what we've done, we substituted F V1 here and F dash V1 over here. Okay. So we have got V2. Now from V2, let's calculate F of V2 and F dash of V2. So F of V2, when we substitute the volume of the value of V2 in this equation. So over there, you'll get F of V2 is equal to 0.0042. And F dash of V2, when you substitute V2 over here, then you get F dash of V2 as 10.918. All right. So from here, you calculate V3, which is V2 minus F V2 upon F dash V2, right? So this comes out to be 0.371 meter cube per kilomole. So as you can see, the difference is not quite much. So we'll take our volume is equal to 0.371 meter cube per kilomole. Now, once we have got our volume in meter cube per kilomole, then we can convert it into meter cube per mole in order to find the molar volume. That's what we had to find. So 1 kilomole and 10 to the power 3 mole. So this can be written as 3.71 into 10 to the power minus 4 meter cube per mole. All right. So this is how we use Vander Waals equation to determine volume. All right. In case volume is given and you need to calculate the pressure, then the equation is quite easy. In case the volume is given and you need to get the pressure, so we already have the Vander Waals equation as P plus A by V square into V minus B is equal to RT, right? So from here you get P is equal to RT upon V minus B minus A by V square. Now you already have V, so you can simply calculate pressure from this equation. All right, that is not a problem. The main issue is with volume, since it becomes a cubic equation in volume. So that is a problem. All right.